Hey guys, this is Manish Yadav. It's my first video for EMEC 303 extra credit. So today I'm gonna do the introduction of range Kutha method. So these are the methods I use for solving first order ordinary differential equations that we talked about before, that we takes the term from dy by dx is equals to the function of x and y. Okay, so I just want to show you guys how we get the form that used for the range Kutha method. Like the general form used by the old range Kutha method is like yi plus 1 is equals to yi plus slopes time step size. So this is our this is our next value of function, which is like our function plus slope and step size times of step size. So this is the general equation, this is a general term that used for by the all range Kutha methods. And I think it's instructive to see that the another way this might look. And how that look is, let's say trying to do a small step from I to I plus 1, which is like our function, the value of function to the next value of the function. So we can separate this equation. So we can do dy is equals to dx function of x and y. Sorry, goes to back. Okay, so now we can integrate the both part by I to I plus 1. So we can integrate dy is equals to function of f and xy dx. We can integrate dy by yi plus 2yi plus 1, and we can integrate the x function to the xi to xi plus 1. And so we'll get yi plus 1 minus yi is equals to f function xi to xi minus 1 plus 1 fx function of x and y multiplied by dx. So this is our like slope time step size. This is our like next value. So we can put this value here, which is yi plus 1 is equals to yi plus function of fxy integration y xi to xi plus 1. This term must be look like this, because this is the value of our next function, which is like function plus step size times slope. And this is also the same thing. So this is our function, and which is plus step size times slope. Okay, so that makes some sense. So one way that I can show you that truly makes some sense, that this equation, like this function is equal to this. So we have a slope time distance, like I'm taking an example. So we have a slope time distance. Our slope could be like yi plus 1 minus yi divided by xi plus 1 minus xi. So this is our function, like this is our next slope. So the value of this is the value of the function, and we can multiply this by our step size. So this is, I'm just taking this as example. So our step size is like x I plus 1 minus x I. So if we multiply this term to this, so these got cancelled out, and what we get is just yi plus 1 minus yi. So this is yi plus 1 minus yi after we cancel out this thing. And if we like, okay, so so that's just the another way of saying what we are doing, that this derivative, like this integration makes some sense, like this is equal to this part. Well, there's another way of making some sense, that I have a function. So I have a function, I have a starting point of a function, and I have the slope. So I have the starting point because we had to have our initial conditions for our function, and we have slope. So we have slope just because of this function. The function of x and y is our slope. Sorry. So I have the starting point and I have the function. So we can guess our next value of the function. So we just need to figure out our next value, like the distance. Okay, so we just come along with a slope and or distance. This might be in certain distance, so we can just take it as our new value. No one knows our actual value because no one knows our function, like our actual function is gonna be like in any type, so it might be any kind of this, so but we are just step along the slope. That's going to be a pretty good guess. So this is our y function, and that's we are trying to figure out because we don't know is our actual y function, we don't have it. So this is our pretty good guess at y. That's the idea behind the old Range-Kutta method, is taking a slope and moving along that slope. The only difference between the each method is which slope who we can come up with and what's our estimate with our slope. So again, so this is the general term that used by old Range-Kutta method to figure out our next value, to like for getting the next value of the function. Okay, for our EMEC 303 course, we already have done the fourth order Runge-Kutta method, which is like update in x direction and update in y direction. So which is like update, so xi plus 1 is equals to xi plus h, which is our step size, and for our y direction is like yi plus 1 is equals to yi plus step size times k1 plus k2 plus k3 plus k4. So our k1, k2, k3, they might be like different, so might be like 1k1, 2k3 and 2k2 plus k4, so the value can be different. Okay, so now we are trying to compute our the next value. So we'll take a xy graph. So okay, now so we are going to take a point, like our starting point here, which is our yi and xi. So and we are going to take a step size of maybe like 0.5. So like this, xi plus half, then xi plus 1. So we can take like yi plus half and yi plus 1. Okay, so we are going to start with this point and we are going to compute our value for like k1, k2, k3 and k4 from this one. So let's take this point as k1. Okay, and we are going to take, so consider k2 as our like half, like xi plus half. So we can use k2 at this point, which is our like k2 from k1 to k2, and this slope will be like k1. And we can our so back to the starting point, we can use our we can draw compute our k2, sorry, k3. So we can use like our k3 will be k1 xi plus 1. So this is will be like this. So this is our k3, and the slope will be our k2. And for our k4, so we can consider our k4 also as xi plus 1, or maybe we can take it like xi plus half. So just let's take it xi plus 1. So this is our k4, and the slope will be like k3. Now by computing and adding all these things, we got our actual value, our actual function y, that's we are trying to get. So we can take this slope as phi, because as I already told you, like our next value, like our next function gonna be x yi plus 1 is equals to yi plus phi times step size. So this is our yi, and this is our next function. So we need a slope and times step size, which means like this equations is true.